I think last class we completed the ANSYS tutorial. We briefly went through the ANSYS. If we have enough time, I will go through a couple of other applications, specifically coupling between uh, different kinds of problems. For example, if you have coupling between fluid and structure, coupling between, let us say, structure and thermal part. Okay, so things like that, we will see how to do problems or how to solve problems like that in ANSYS later once we have enough time. Now let's see here. Let's go for ANSYS numerical analysis. Okay, so let's go for a new lecture today. Okay. So we will move to a new chapter today. Hopefully, yeah, okay. Page. All right. Okay, so the second chapter is mainly going to be on materials and material selection. This chapter is also theoretical. Once we move to the third chapter, then we start to solve problems. I will try to finish this chapter as fast as possible. Okay, the outline of the lecture, we are going to discuss what is the importance of the materials and the properties of the materials, different types of materials. Okay, in the last part of the chapter, we will go through Ashby chart and see examples on how to select materials based upon properties. We will derive what is called as material index and then try to select the properties. Let's see here. Let's see one example here. Hip implant. If you might have seen that old people usually have problems in joints and bones. Sometimes these bones they fracture. Also, it is possible that when two bones, you can see here, for example, here, the thigh bone here and the hip bones, the joint has ball and socket joint, and between the bones there is a cartilage or some kind of a uh, lubricating material. Okay, so this is a biological material, and over period of time what happens is this lubricating material goes off, wears off, and because of that the bones start touching each other, and it might cause certain nerves to be caught here and it leads to too much pain. So they do what is called as the hip replacement, where they cut off the bone, make a hole in the thigh bone, and then replace it with a metal which has a ball, and they will also replace the hip bone in this part with some kind of a artificial material, and this is called as the hip implant. Now, in order to select a material for such a hip implant, there are a couple of properties uh, we should be aware of. Can you guys tell me what kind of properties we are looking for in hip implant? What should be the property of the material, of the materials we are looking for in the hip implant? Are you guys listening?
Yes, doctor. Yield strength.
Pardon? Can you tell me one example of a property?
Yes. Yield strength.
Yield strength. Okay. Why yield strength is important? When you are putting some other material inside your body, what is the most important property you would be looking for? For example, not only hip implant, maybe you want to put a piece of metal, let's say in a person's hand, broken hand. What is the most important property you would be looking for? It should be chemically inert. Okay, if you put any foreign material in your body should not treat that material as a foreign body, and it should not start attacking it. Okay, so your body is made out of living cells, and for example, if anybody gets infected, what will happen? Your body will fight back against the infection. So your body is trying to react to foreign materials which are introduced into your system. So first thing you have to ensure, in the case of hip implant, for example, it should be inert with respect to the body functions. Your cells should not attack these parts, and they should not take these parts as foreign materials. So this is a very, very, very important property. Besides that, your implant should have properties very similar to your bone. If it is much stronger than the bone, then what will happen? Since your body is a living structure, what it will do? It might make some changes with respect to the bone structure here. If your implant is stronger than the bone material, here it is possible that the bone material around, since these bones, they can grow or deteriorate, some of the bone material may just get deteriorated, will reduce in size, since your metal part can carry more weight. If that happens, then again bone fracture is possible. The hip implant which is drilled into the bone here, on the thigh bone here, may come out. So there are other problems. Unlike your structural problems, in biological parts, there are much more involved problems in the selection of the material. Okay, so these are some of the important biological properties. Besides that, we have to ensure that the strength of the material is very close to the strength of the bone here. In that way, it will simulate the bones. Okay, all right. So again, here we can see we need good lubrication. Some of the material which is introduced here must have good lubrication, so that the joint will not have any friction and does not lead to any damage. Okay, it should have very good mechanical strength over many cycles of load. Okay, fatigue should not lead to damage of the material. Biocompatibility, we already talked about it. Because a typical hip implant, you can see here, it is not just made out of a single material. There is a metallic ball, then there is the fixing agent, and then fixing agent in dark blue color, and there is also some kind of a cup which takes care of the lubricating properties. And you can see the fixing agent all around here. Okay, so this is a very simple description. Again, you can see various parts. You have the stem ball. There is a polymer acetabular cup. Then there is the liner here. You can see specifically the liner is porous in structure, so that the bones can grow into the porous structure, and basically the bone and this material will meld together. Okay, So the design is much more complicated. Again, you can see there is a porous structure here given here so that the thigh bones can grow inside of these pores and there will be a bond created between the bone and the porous structure here. Okay, another example, we have various classes of materials. Here we have seen some kind of a ceramic material, metals and alloys, plastics, again, examples of polymers, ceramics, metals. What are the different categories of materials, engineering materials you have? You might have learned this in your materials engineering course. What are the different categories? You already have metals and alloys here, polymers, ceramics, and if you mix any of these engineering materials, you get what is called as hybrid materials, and those are composites. Okay. Okay, so these are some of the classes. Again, you have some special kind of materials. Basically, a semiconductor is also classified as a ceramic material. What is a semiconductor? Can one of you tell me? What is a semiconductor? Are you guys there?
Silicon.
Silicon is an example of semiconductor. Where do we use these materials? In which
Electronic
application?
circuits.
Electronics, in your computers. Okay, anywhere you have control system computers, any kind of electronics, there we may use semiconductors. Okay. All right. So let's see some of the properties of metals and alloys to be more accurate. What is an alloy? How will you know something is an alloy? Okay, the examples you are given here: aluminum is a metal, steel is
When
an
it
alloy.
is has some impurities.
Impurities. All things have impurities, but how do we make alloys? For example, if I make pure iron, if I try to make pure iron, manufacture it, you will see that I can produce iron today with today's technology about 96% pure, maybe 95% pure. Still, it has impurity, but we don't call it an alloy. Pure iron, we call it as iron, metal. What is an alloy? Anybody? An
When it
alloy,
has some percentages of impurities.
what? All things have impurities, I've told you, right?
I mean higher percentages, like
Higher percentage.
more than.
We introduce other materials into a solid solution. For example, in your materials engineering course, you might have learned something about solid solutions. What is solid solution? Do you recall it? You take different metals, melt them, and mix them together. So at very high temperatures, when you take and mix them together, for example, in steel, you have different elements, specifically iron and carbon is wantedly introduced. Carbon is wantedly mixed with iron to up to a certain percentage. Maybe if it is a low carbon steel, 2% carbon mixture leads to steel. and this is called as a solid solution. Similarly, if you take gold, gold is usually mixed with copper. So two different elements, they are mixed together and then leads to a solid solution. In the case of solid solution, there is no chemical reaction between two different elements. Rather, the atoms of the different elements, they go and sit in particular places in your structure. In your structure, when I say structure, I'm talking about the face centered cubic structure in BCC structure, etc. They go and occupy certain positions, and these positions could replace existing atoms. For example, in gold, they could replace existing positions, and in the case of steel, carbon atoms occupy certain interstitial positions. Okay, so this way they create a solid solution. Okay, so again, try to recall what is a solid solution. Solid solution is the same as the alloy. Okay, so in an alloy or a metal, usually the atoms are arranged in order in FCC structure, BCC structure, etc. Especially when they solidify, they have an orderly structure, and usually they are in a very dense pattern, leading to very high density in the metals. Metals and alloys are usually very stiff and strong. They are ductile, leading to plastic deformation, and they have very good conduction properties. The conduction properties could be electrical conduction or the thermal conduction. Okay. Now, since second, this is not working. Okay. Now, since in the metals you have, if you take a metal and if you see the microstructure, okay, so let's say this is the surface. On the surface, if you see the microstructure, you will have many grains like this. And let us say if you take each grain, you might see the BCC structure, or in the case of steel, specifically it is a BCC body centered cubic structure. Maybe in the center you have, I'm just drawing a 2D version of the BCC structure. You have the atoms located in particular location, the nucleus of the atoms specifically, and then you have electrons, sea of electrons around it. The atoms are able to vibrate from its nuclear position. They can vibrate around depending upon the temperature. Okay, since they can vibrate around the nucleus of the atoms, they can vibrate around. Therefore, it is a very good thermal conductor. If the nucleus of the atoms cannot vibrate that easily, then it becomes a very bad thermal conductor. It is a good electrical conductor because the electrons are free to move in. Okay, they are also free to move in, and therefore it is also a very good conductor of electricity. So this is the general case. Now, if we go to the more examples here, let's see. So we don't have. If we go for ceramics, on the other hand, this is the case of metal ceramics. In the ceramics, your atoms are not free to move around. So in metals, you have what is called as metallic bonds. In metallic bonds, your atoms are free to vibrate and electrons are free to move around. On the other hand, if you take ceramics, you have covalent bond, or ionic bond or a combination of these two in ceramics. Okay, whenever you have these kind of bonds, they do not allow free vibration of atoms, they do not allow free motion of electrons, and therefore ceramics are usually very good insulators, and they have very bad conduction properties for electricity or even heat. Okay, so they are very good thermal insulators and electrical insulators. Okay, so we know the difference between metals and ceramics. So let's go forward and let us try to identify materials. So how do we identify materials in engineering? Through standards. And there are many institutes which publish material numbering systems or identification systems. So basically these professional organizations give you a numbering system through which you can identify each material. So Society of Automotive Engineers, SAE, they publish their own standards. AASI, they publish their own standards. Again, UNS system is published by SAE and AASI together. Okay. ASTM also, they have their own specific standard. Okay. We are going to see specifically the unified numbering system, okay, which was developed by SAE in 1975. Let us take steel and alloys. How do we identify, for example, steel and its alloys? They are, say, iron and alloys with carbon, which gives you steel. G is used to identify usually carbon and alloy steels. This is the letter we identify steel with. Usually the UNS system has 5 numbers, okay, 5-digit numbers, and before that you have a letter prefix. So first we go through this letter prefix. G stands for carbon and alloys, A for aluminum alloys, C for copper, S for stainless steel, and we use several other letters. We will see that letter later. Okay, so in the next slide we have the description. For example, W is used for specifying welding materials, T for tool steels, and you can see here S again is used for heat and corrosion resistant stainless steels. S for stainless steels. G is for low carbon steels and other kind of steels, alloy steels. However, S is specifically for stainless steels. K, you can see here different miscellaneous steels and ferrous alloys. Any kind of ferrous alloy also can be represented here with the letter K. Cast steel with J letters. H for hardened steels, and G we can see generally other steels. Okay, so we have this table. Through this table you can identify which letter refers to which kind of materials. A much more detailed view is given here. If you zoom in, this is very small. Unfortunately, I could not fit the entire table into a page. You can see here you have 5 digits, letter followed by the 5 digits. If your material is identified with the UNS numbering system series with this particular range, then it refers to this particular element. Okay, E stands for rare earth materials, P for precious materials. You can see much more detail. Precious materials include gold, indium. So these are very difficult to find materials and are expensive. And that even the rare earth materials, as the word says, these materials are very difficult to find, and you will see these materials are extremely expensive. Have steel alloys in the list. You can see miscellaneous elements again. So each element in your periodic table, they are identified. Zinc alloys, other kind of alloys, you have tungsten and various kinds of other elements which are used. Okay, so this is with respect to the first letter. Okay, so let's go for steels in particular. And first, for steel, we will use the prefix G, okay, followed by 5 different numbers. What those numbers refers to. The first 2 numbers, they refer to this particular classification here, where it provides what is the additional element added into the alloy, especially with respect to steel. So 10 stands for plain carbon, no other element is added. And if you take, for example, 43, G43, you are going to see this material is quite often used in engineering, especially in automobiles and many other applications. Nickel, chromium, molybdenum, these are the additional materials which are added to the steel material. Again, various other numbers refer to what is the material we add. So this is the first 2 numbers following the letter. After this, we have 3 more numbers. We will see the second 2 numbers, second pair of the numbers indicate the carbon content in hundreds of a percent. So let's take this example here. G52. 52 refers to chromium as the alloying material, additional alloying element in steel. And 98 stands for 0.98% of carbon. Okay, so what is 6? 6 is usually used for additional special situations. It could be anything related to special elements which are added or some other manufacturing processes used to identify the particular material. Okay, so why is steel extensively used within the engineering field? Because it is widely available material all over the world and it has very good properties, preferable properties we want. What are the preferable properties? We have high strength. Okay, steel usually has very good high strength, yield strength in particular. Okay, and the ultimate tensile strength as well. High modulus of elasticity. Okay, this is very much essential, especially if we are looking for very good stiffness properties. Stiffness is controlled by elastic modulus or Young's modulus E. How do we define stiffness? Stiffness K or small k is defined by force over any deflection delta. Okay, so this particular, if the k value is very high, that means your deflection value is going to be very small for a given force. And this is the property we require in most of the structures. We do not want the structure to bend too much or to undergo deformation too much under the application of the load F. So if your E value is pretty high, the K value will also be high. So in the case of a simple axial rod case, if you have apply a force F, in this case we can calculate K as E times A over L. So this is the stiffness property. Okay, take this for granted. So here if E value increases, then the K value will also increase. High hardness. This property is, hardness is the property where it does not allow the surface of the material to be scratched or dented locally. So why do we need this high hardness property? That if the hardness of the material is high, it increases to improve fatigue properties. In chapter 5 we will see. So hardness is often related to fatigue. So whenever you apply a cyclic load on the metal, it will easily break. So let's take a very simple example. You have a piece of metal wire, okay, and I ask you to break it, very thin piece of wire. I ask you to break it just by using your hand. How will you break it?
Twist it.
Twist it. So you will twist it up and down. What you are doing here, you are applying a bending moment like this, and then you will reverse it and apply a bending moment like this, and you will repeat this cyclic load often. So when you repeat this cyclic load, what happens? It will break very easily. Try to break the same piece of wire by just applying tensile load. You will have to apply very large loads, and then you will be able to break it. However, by just using your hand, by applying cyclic load, you can break it very easily. This is called as fatigue. Okay, and that happens due to very small cracks present on the surface of the wire, and when you apply the cyclic load, these cracks that they start propagating, and then the wire breaks, and this is called as fatigue. If the surface hardness is very large, these cracks will not be forming in the first place, and the fatigue cannot happen. Okay, fatigue, or at least life of the specimen, increases even under cyclic fatigue loads. The higher the hardness, the better. Okay, steel has very good hardness properties as well, provided we do not have any of these cracks. It operates at high temperatures. Okay, it has good properties even at not very high temperatures, but good properties at medium high temperatures. The disadvantage is it is very heavy. We cannot use steel, for example, in construction of aircraft structures. If you want to build the body of the air of a plane, you will prefer an aluminum alloy in compared to steel, because steel is very heavy. Okay. Also, the strength to weight or strength to density property, for example, in applications like aeroplanes, you want the ratio of yield strength to density to be very high. In the case of steel, in comparison to aluminum, this ratio is small. Now, why do we consider this ratios? High strength to low corresponding lower density. These ratios tell you how much material we need to use to have particular desired properties in a structure. And we are going to use ratios like these in Ashby's chart as well, okay, for selection of materials. We will see that later. By adding different amount of elements, for example, nickel, chromium, molybdenum, okay, etc., we also get very much desired properties in steel, and we can do these things easily with steel. Okay, for example, if you add chromium, leads to corrosion resistance, okay, and which is a very important desired property in the material. Has very good ductility, machinability. You can easily cut the material, form it into different shapes. It has very good ductility. What does it mean? You can form it into different shapes by applying forces, or heating and applying forces, making it into different shapes. Also has good corrosion resistance, and by alloying, you can even increase the corrosion resistance properties of steel. So this is why we use steel extensively. Now here we are going to see an example here where we increase the strength of steel several fold, okay, by just doing a combination of thermomechanical treatments and alloying, okay, for steel. Now, if you take your simple plain carbon steel or the mild steels, okay, they are very easy to form it into different shapes. So usually plain carbon or mild steels, medium carbon steels, we can use to form it into different shapes in your car body. For example, the panels used in the doors here, the front part of it can be covered with the uh, the hood here, okay, formed all by these kind of materials. But when you take the frame of the body here, so this is a frame, you see the skeletal structure, this forms the frame. Especially take this part where you have the front uh, glass being fixed here. Now this part of the skeletal structure or the frame of the body of the car needs to be made out of a certain material which has very high strength. Why? This is a critical part. In case of accidents, if this skeletal structure of the car gets bent very easily due to high stresses, then the person sitting inside the car, the driver, will lose his life instantly. You do not want this to happen, and therefore this is made out of this kind of structure is usually made out of very high strength steels. So these kind of high strength steels, they are called as AHSS, advanced high strength steel. Usually the yield strength of these kind of materials, they are greater than 500 megapascal. Now, what is the usual yield strength of steel? If you take the low carbon steel, medium carbon steel, the usual yield strength, we are going to usually refer to the material properties with the letter S and any subscript. Y stands for yield strength, U stands for ultimate tensile strength. Okay, so the SY value for mild steel, medium carbon, low carbon steel or medium carbon steel, usually it is in the range of 200 megapascals. Okay, so this is not very high strength. In applications like these, this is very dangerous. So the automotive industry has come up with processes to manufacturing processes for steel to create very advanced high strength steels with greater than SY value being greater than 500 megapascal. Nowadays, it can reach up till 2 gigapascals. Okay, the yield strength can even go up to a range of 2 gigapascals. So this is very high strength steel. So some of these examples are your dual phase steels, okay, and press hardened steel. There is also multiple phase steels, and you can do a Google search. When you do a Google search, it will give you what are the different types of advanced high strength steel. For example, if you take dual phase steel, there are two different phases. By adding different elements, you create these two different phases. And in dual phase steel, even though the yield strength is very high, usually it also has a very preferable high energy absorption property. Now, there are two different properties in materials which are usually inversely related. For example, yield strength and another property which is called as fracture toughness. What is fracture toughness? You can think of it as the ability of the material to absorb impact energies without breaking into pieces. If you take a ceramic material like glass and drop it on the floor, due to impact force, it will break into pieces. That means the fracture toughness of glass is very low. On the other hand, if you take a material like steel, mild steel or low carbon steel, and drop it on the floor, probably the floor is going to break. Okay, so your mild steel is able to absorb all the impact energies without undergoing fracture. Now the relationship between the yield strength of the material and fracture toughness usually is, if you increase the yield strength of the material you by a process, by some mechanical process, okay, without adding additional elements. For example, I can increase the yield strength by simply deforming the material beyond plastic deformation, and then I will be able to increase the yield strength. Okay, we will see that later. How do we do that? There is a process called cold working by which we can increase the yield strength of the material. But when you do that, when you increase the yield strength of the material, automatically the fracture toughness goes down. As you increase it, the material will become more and more brittle than being ductile. Then, because it gets brittle, we will have reduction in properties of fracture toughness. But the automotive industry has come up with methods where they can increase not only the yield strength, they can also increase the fracture toughness significantly. Okay, both can be increased significantly by playing with the microstructure of the materials. Okay, so when you have both these properties in advanced high strength materials, then it can be used in applications like these, where these materials do not fracture upon impact. Not only that, it does not deform easily because it has very high yield strength. So when this is the case, then there is safety for the driver using this particular material here in this application. Okay, so in any safety related applications, we may go for advanced high strength steel. Okay. Okay, so if you do a simple Google search, okay, here, if you do that, you can specifically see in automotive industry, this is widely used, advanced high strength steel. Let's click on it. So you can go through some of the important information regarding this. I'm not going to go through this. So there are many websites like these which provide specifically very good information on advanced high strength steels. Okay, let's go back to the numbering system now. If you take aluminum, for example, how do we identify aluminum? Again, it has a letter A. Any numbering system starting with the letter A represents aluminum, followed by the 5 digits. Okay. The first number following A usually indicates what is the processing which is used to produce this material. We will see exactly what is processing. So this is the first number. Any number in this location X right after the letter represents processing. So what is the processing? Any number between 0 to 6 tells you that aluminum was produced by a method which is called casting. Anything between 7 to 9, it shows you followed by casting, some kind of a mechanical deformation process was used. For example, it could be rolling, it could be any other process like extrusion, etc., in forming the raw materials of aluminum. If it is between 7 to 9, and usually it is called as wrought aluminum. Okay, so when a deformation process is used, it is called wrought aluminum. The second number indicates main alloy group, specifically what is the additional element which is added. That is given by this table. So if it is 1, it represents only aluminum, 99% purity. 2, copper is added to the alloy, manganese is added to the alloy, if it is 3, etc. In a similar way, you have other materials. Okay, so the second number we have seen. Third number is used to modify the original alloy or to designate impurity limits. And the last two numbers refer to some special group again. Okay. So what are the preferred properties of aluminum? You have very good strength to weight ratio. Okay. So that means SY over rho. In compared to steel, the property here, this ratio is very high in the case of aluminum. Corrosion resistance, because naturally aluminum will be covered with a layer of aluminum oxide and it will prevent any kind of corrosion. It has very high thermal conductivity, electrical conductivity, and we can use it in appropriate applications. It is easy to machine and cast, but it has certain disadvantages. It is very difficult to weld and not as easy as steel, okay, in case of aluminum. Also, in comparison to steel, aluminum has much less fatigue life. Okay, so fatigue life is lesser than that of steel. Aluminum is less than that of steel. Well, okay, so we have seen what the numbers refer to. Let's take an example, A96061 aluminum alloy. So this 6061 aluminum alloy is very frequently used and frequently referred in many applications. 9 here refers to the processing used, 6 here refers to the element which is added. So the second number here you can see magnesium silicon alloy. Okay. We can also have ceramics. We have seen what are the examples of ceramics. Glasses are ceramics. Your bricks, which we use in construction, is ceramic. Cement is ceramic. Okay, so all these materials are ceramics. Usually ceramics have ionic or covalent bond or both. Combination of both, and even a single bond, if you take, it can have a certain percentage of the bond as ionic and a certain percentage of the bond as covalent. Okay, so this means the position of the atoms cannot be changed. The electrons are stuck to a particular atom and they cannot move around, which means they are very good thermal and electrical insulators. It is also very corrosion resistant because these electrons cannot move around. Again, it does not lead to chemical reactions very easily, and therefore it is very good. It has very good corrosion resistance. Now, since the atoms cannot move around, the bonds cannot change that easily. That means again it has very high stiffness, very high strength, and hardness. But all these properties obviously lead to brittleness of the material. So ceramics are usually very brittle, cannot undergo plastic deformation, and it will undergo fracture catastrophically. So we cannot use them under tensile loads. So usually we do not use ceramics under tensile loads. However, we use ceramics under compressive loads. Cement is extensively used under compressive loads. All your building structures, for example, they are made out of cements and bricks. They undergo compressive loads and they are still used under compressive loads. They are also used as thermal insulators in ovens, etc. You will see ceramics are extensively used. Sometimes a ceramic lining can be given to metals and alloys to protect metals and alloys from very high temperatures. Some examples: alumina, silicon dioxide. So these are some ceramic materials. Now, if you take silicon carbide, this is also a ceramic material, but it has very high strength and very high hardness. And therefore, it is used as a tool material, cutting tools for metals. Okay, so if you take your cutting tool in lathe, it's usually made out of silicon carbide or silicon nitride. All these materials are cutting tool materials. There is glass, which has very good transparency. Okay, so we use it in different applications, but it is very brittle. But with combination of other materials or by using some kind of fibers, we can increase the fracture toughness of glass as well as in your automobile applications. Some examples: bricks, tiles which we use, your cups, glass, all these are ceramics. Okay, so this is another category, polymers. You might have seen specifically all the plastics which you use in switches, etc. These are all made out of polymers. Polymers can be usually classified into three categories. One is thermosets, another is thermoplastics, and then the third category is elastomers. Usually these are naturally occurring materials. Thermosets, you might have seen, these are the materials. Once if you melt it, they form into a particular shape and they are set in that particular shape. If you heat them again, they will burn and become black in color. So these kind of materials are often used in making your switches. Okay, so the switch which we use to turn on your lights at your home, they are made out of thermosets. Thermoplastics are materials which we can melt and form it into different shapes again and again. Elastomers, on the other hand, are usually materials like your rubber, which are extracted from trees. If you do not know, natural rubber is extracted from trees. Okay. Okay, so let's see here. Usually, polymers have very large molecular structure. You will have a long chain carbon backbone on which additional materials can be there. For example, with the carbon, you can have oxygen, nitrogen, silicon, other materials bonded to it, covalently bonded to that. And the dominant force since we have very large molecules within polymers, the dominant force here is the van der Waals force or the secondary forces. What is a van der Waals force? Unlike the primary forces like your metallic bond or your ionic or covalent bond, which are primary bonds, van der Waals force are classified as secondary bonds, and usually these are weak. Primary bonds require very high energy to break them. Secondary bonds require much lesser energy to break these bonds. Van der Waals forces are usually between two molecules. Okay, so when we have forces between two molecules, that is called as van der Waals force, and this is weak kind of force. So this is the dominant force within polymers, and because of that, your polymers can be easily bent into shapes with a very less amount of force in comparison to alloys or ceramics. Usually these materials are ductile and they have insulation. Now, since the molecules have covalent bond within the molecule, that means it has to be a good insulator. Okay, it has low density because of these van der Waals forces, very large molecular structure. So some of the examples of the polymers here. So where do we use polymers? Again, some of the applications widely used in many cases. Even your tire is made out of rubber. This is also a polymer. There's another disadvantage is that polymers cannot operate at very high temperatures. Even if you go to a temperature of 70 degrees centigrade, these materials undergo probably chemical changes and it will get burnt, and it will lead to very less strength at these lower temperatures as well. So in case of polymers, often they use creep strength of the material. Okay, creep strength of the material at high temperatures. So what is the creep strength? So let's see with a graph. If you look at, let's say, the yield strength of the material and plot it as a function of temperature, okay, you are going to usually see for any material the yield strength of the material will decrease. Okay, now this is the property even for metals and alloys. Let's draw another graph and we are going to see the effect of the yield strength over time. So instead of temperature, over time, keeping the temperature equal to fixed here. So fixed so it could be at a higher temperature. Let's say for plastics, it could be around 70 degrees centigrade. And in the case of metals and alloys, it could be very high temperature, 650 degree centigrade. And if you look at the yield strength of the material over a large amount of time, it could be several days or even months or years. Okay, so depending upon the application, it could be different. And if you see, the yield strength of the material will go down over the period of time. So under the same load, okay, now here we are assuming there is no chemical deterioration of the material, no corrosion of the material, but just by application of the force, a constant load. Okay, force is constant. We are going to assume by applying a constant load over a very long period of time, what you observe is that the yield strength of the material goes down and it reaches certain minimum value. So in the case of plastics too, it will reach a minimum value, and this yield strength we are going to call it as creep strength of the material. And in most of the applications, especially with static loads where force is constant, we will use the creep strength of the material for calculations and design rather than using the original yield strength at room temperature. Okay, so this is what we do with plastics, and we can also do this with respect to metals or alloys. Okay. So let's move composites. What is a composite? Can one of you tell me what a composite is? Anybody?
A material which is made of the matrix and
Very good. Very
reinforcements.
reinforcement fibers. Okay, usually matrix material and then reinforcement material in terms of fibers. We can use fibers, or it could be also particles. So these are, or it could be sheets of materials, okay, used as reinforcement. Okay, reinforcement. So this is called as a composite material. Usually these fibers, particles, they are of macroscopic size, not microscopic. Okay, it is not microscopic. What is the difference between a solid solution, that is the alloy, and a composite? In the case of solid solution, you cannot see the individual elements separately when you look at the cross section. In the case of composites, even with your naked eyes, you will be able to see the fiber material, the particles or sheets of materials which are introduced into the matrix material here. So let's go to an example. Your any building structure, if you look at the columns and if you are able to break the column and look at the cross section, you are going to see cement matrix. Embedded within the cement matrix, you have long steel rods protruding out. Okay, so these rods act as fibers which provide any tensile strength required for the structure. So this is an example of composite material. We can use similar composite materials in different applications. For example, your carbon fiber reinforced polymer. What is it? You have a polymer matrix. Usually polymers have very less strength, reinforced with the carbon fibers. Carbon fibers have extremely high strength. Okay, so what is the typical yield strength or the tensile strength of carbon fibers? See, for steel, you have seen advanced high strength steels can go up to 2 gigapascals. But if you take carbon fibers, the strength goes to 1 to 3 terapascals. That is the strength of these carbon fibers, but they are very expensive materials. So what is the difference between a gigapascal and a terapascal? Can one of you tell me? What is gigapascal?
10 to the power 9.
10 to the power 9. And what is terapascal?
10 to the power 12.
10 to the power 12. So in this case, you can see 1000 orders of magnitude. Okay. Now we have seen that very advanced high strength steels have only 10 power 9. But when you take carbon fibers, it is 1000 times more. So in space applications, if you take your spaceships, the front part of the cone of the spaceship, you will see they are reinforced with carbon fibers. Okay, in those kind of applications, expense or cost is not an issue, and therefore we use the very high strength material. So this is the reason why we use carbon as the fiber to reinforce plastics, because of its very high strength. Another advantage, this is a very good insulator. It can take extremely high temperatures. Okay, even in comparison to steel, this has very good properties, even in comparison to steel. Okay, all right. So some of the applications we have seen, composites. Let's go for the standard tensile test. I will quickly go through this since you know all these from your materials engineering course. I'm going to directly go to the experiment and the properties which are extracted. You know what is stress? Stress is defined as, at least the average stress, engineering stress is defined as the force over initial area of cross section. So in the tensile test, you have a specimen like this. You know what is its initial area of cross section. And since we know what is the load we are applying slowly on the tension test specimen, based on that, we can calculate what is the stress. In tension test, what do? We mount this material in a testing machine and slowly increase the load, and then we find the properties. Okay, so let's go here. Let's see, what do we have here? Test. Okay, tensile test. I'm going to play this tensile test. Please confirm if you can hear the volume. Can you guys hear the volume?
Yes, Doctor.
So let me increase it just in case. Okay, let's play this.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. the 0.2% proof strength RP 0.2 is equal to FP 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Okay, so we have gone through the tensile test. Two materials were tested in the video. One material is steel, the second material is aluminum. Okay, and the stress strain diagram for each of this case is different. Different in what way? Let's go down here. So in case of steel, we had the stress strain diagram in tensile test where we increase the load quasi-statically. Okay, quasi. What is quasi-static? We increase the load slowly, slow enough. Slow. If you increase the load very fast, then you will get different stress strain diagram. Okay, so at a slow speed, and then we got a response like this, almost a vertical line, and then it goes down, then it does something like this, then we have fracture. So in the case of steel, we have the upper yield point, so let's write it as SYU, and the lower yield point here is LY. Okay, then we have the ultimate strength, then the fracture strength. This is for steel. In the case of steel, it was easy to identify the upper yield point and lower yield point. Just from looking at the graph, I can get the highest point here, lowest point here, and from the force diagram, and immediately calculate these values. However, if you take for aluminum, on the other hand, we had a different picture. We do not have these upper and lower yield points. In the case of aluminum, we had a smooth curve. Then smoothly goes here like this. Okay. And then fracture. Okay. So where is the yield point? When it smoothly transitions from elastic to plastic region, we do not know where the yield point is. So the general procedure is we take a strain of 0.2%, that is 0.002 as the strain, draw a line parallel to the initial line, and wherever it intersects, we will call this as the yield point. So that is the difference between aluminum and steel. Not every material, it is apparent that we have a yield setting in. Okay, so besides that, why does steel have this variation while aluminum does not have? Okay, so there is something going on inside steel in microstructurally that does not happen in the case of aluminum. So what is happening here? Here what happens is the dislocations they do not plastic deformation, that is slips. The slip phenomena does not take place over the entire cross section of the steel specimen. It happens, okay, so this particular region, it was called as Loder's band. If you carefully listen, then there should be an apostrophe here, Loder's band. You might have heard of this, the lady saying it is Loder's band. Here the region, in this particular region, plastic deformation does not take place uniformly along the length and the cross section. Rather, it takes place at specific locations locally. And because of this, what happens in this region, if you zoom into this particular part, what you are going to see is the force increasing in a zigzag fashion and decreasing, increasing and decreasing, increasing and decreasing, increasing and decreasing. So this is what happens in the Ludus band. Why does it happen? First, what happens is, first when it increases, the dislocation is not moving. Local dislocations are not moving. Then what happens? Suddenly the dislocation moves locally, and then in some places locally, then it decreases. Then what happens? More dislocations are created and they do not move. So now it increases. Again, it decreases because now the dislocations are moving. So this will continue happening until the entire cross section along the length also entire cross section undergoes uniformly plastic deformation. When the entire cross section reaches uniform plastic deformation at this point, then what you have is strain hardening phenomenon. So here we have increase in the stress. To cause any slip, now we will have to increase the load. Okay, so this region is strain hardening region. Okay. So this should be enough, and then once it reaches necking, at the point where the necking is there, the area of cross section significantly decreases, and therefore it looks like the force is also decreasing, and because the force externally applied load taken by the specimen is decreasing, the stress seems to decrease. Why? How do we calculate this stress? This stress is actually calculated as the force taken by the specimen F divided by the actual area of cross section. Okay, so because we are considering the area of cross section as constant, it appears that stress is also decreasing because F is decreasing, A naught is constant. Obviously, sigma will decrease, the calculated sigma. But this calculation at necking will be very wrong. Why? Because since the area of cross section is significantly decreasing, we cannot use this area. That is a definition for true stress. So if we define true stress as F over instantaneous area of cross section, and now if you plot the true stress here, you are going to see completely different behavior. Let's draw it in red color. If I plot the true stress here, let's see here. If I plot the true stress up till this point, from 0 to perhaps up till this point, you will have the same true stress, but it will start to become different at this point, and my true stress, you will see it is continuously increasing. When I use the actual area of cross section, instantaneous area of cross section, the stress is increasing, and because of that, the fracture takes place. Okay, so this is the stress strain graph. We have extracted all required properties. We have the yield strength, ultimate tensile strength, fracture strength, and then we also can extract up till the proportional limit here. Proportional limit, we will be able to extract Young's modulus. So initially we have linear elastic response, and that we can extract the property which is called as Young's modulus here, and also for aluminum we can extract. Now if you carefully look at it, this is the point of proportional limit, Up till the proportional limit, E value is valid, but between the proportional limit and the yield strength, we have this blue region here. This is a non-linear elastic region. Okay, so now we go for Hooke's law. The Hooke's law is valid up till proportional limit. Hooke's law. Is valid only up till proportional limit. That means, let's assume corresponding to proportional limit, we have the property is proportional, stress proportional limit. Okay, and then we write the Hooke's law. Sigma is equal to E times epsilon. This is called as Hooke's law, at least 1D Hooke's law, and it is valid when your sigma is less than or equal to S proportional limit. If it is greater than proportional limit, then this is not valid. Hooke's law is now no longer valid. We may have a nonlinear elastic region or a plastic deformation region where your sigma becomes a function of strain. For example, you can have power law. Power law, for example, can be expressed as A epsilon raised to the power n. Okay, n could be any number. It could be 1, 2, 3, or it could be even real numbers 1.2, 1.3, etc. And it becomes a completely different equation, especially if sigma is greater than the yield point. Okay, so we cannot use the Hooke's law blindly. You have to know that Hooke's law is valid only up till the proportional limit. So let's go back to the slide. So we have defined what is stress. The engineering stress is defined as the force taken by the tensile specimen by the initial area of cross section. Strain is defined by the L minus L naught value over L naught. So this is engineering strain. Just like we defined true stress, there is also true strain definition. We will come to that later. Okay. So for ductile material, we have seen it has a huge plastic region. On the other hand, for brittle material, does not have any plastic deformation. And in fact, you will see that if you draw to scale, the yield point and the ultimate fracture point, they are extremely close to each other in the case of brittle materials. For aluminum, we have already seen, we draw a parallel line to 0.2% and then figure out what is the yield point. So this is the according to the standards. So we have gone through this. Hooke's law, we have already expressed that. Okay, we have 5 minutes, so I will try to cover a small part here and then we will stop. Okay, so under tensile load, we have seen how the material behaves. What about compression? Okay, also under tensile load, we have seen another important property. So I forgot about that. So rather than going here, it's better to show from a picture. If you take any specimen and look at the surface of the specimen, the fracture surface, for example, this surface clearly shows here. You can see the cup and cone fracture for the steel specimen. Yeah, right. It is at 45-degree angle, and this makes sense because why there is a 45-degree angle? Because with respect to the tensile load direction, at 45-degree angle, the shear stress will be the highest value. And if you recall from your solid mechanics course, you can argue based upon the Mohr circle that shear stresses are maximum at 45-degree angle, okay, with respect to the principal stress direction. In the case of axial load, the principal stress direction is along the direction of the load, okay, tensile load. If you take the brittle material, on the other hand, the fracture surface is flat. But when you looked at aluminum fracture surface, so let's see here, this is for steel cup and cone fracture, and let's take aluminum fracture surface instead of having the cup and cone fracture. Let's see here. You are going to have just a plain 45-degree angle of fracture. Unfortunately, it's not shown. Maybe we can see an example here. So this is all cup and cone fracture. Write it as aluminum fracture. Hopefully they show it. Okay, I think this is the best picture we have. Okay, so for now, this is the best picture we have. If you look at the aluminum fracture surface, it's just going to be 45-degree angle fracture. Okay, not cup and cone fracture. Okay, so it's slightly different in case of aluminum. Okay, now we go back to compression. What happens in compression during compressive load? So instead of having necking phenomena, what you will have is a bulging phenomena under compressive loads. There is also another phenomena which can happen, which is called as buckling. Now we will discuss these two phenomena in the next class on Thursday. Since the time is up, I will try to finish this chapter within this week, and we need to quickly move to the other chapters. Okay, any doubt up till now? If you do not have any other doubt, I'm going to stop right here, and we will meet again on Thursday. So see you guys then.